Hello and welcome to the lecture of linear algebra. In this lecture, we'll talk about application of eigenvalues and eigenvectors to discrete dynamical systems. Generally, eigenvalues and eigenvectors can be used to study the long-term behavior of any discrete dynamical system. As we have seen in the previous lectures, that discrete dynamical systems can be represented, or a dynamical system can be represented by a difference equation, which is of the form which is known as x plus 1 is equals to a times x of k. Now, this form we have the numerous examples on this form. One of the example was the migration in population from rural to urban side, and we studied the long-term behavior in one of our previous lectures. So generally the vector x of k gives information about the system variables at the kth pass. So if we do a predator prey to give an understanding of how eigenvalues and eigenvectors work in study of discrete dynamical system, we consider what we know as a predator prey system. So before we do that, since we know, but before we go to the example of predator prey system, first we need to understand is to consider that A is actually diagonalizable, and we have studied the procedure of how diagonalization can be achieved for this matrix, and we have n linearly independent eigenvectors v1 up to vn with the corresponding values lambda 1 to lambda n. Okay, now so if we for convenience we can assume that lambda 1 is the largest value, the magnitude is the largest one, so we arrange those eigenvalues in descending order, and we know that since they are linearly these vectors are linearly independent vectors, and they span Rn. Okay, as you have seen in our previous lectures, that these eigenvectors corresponding to the eigenvalues of the matrix A can span Rn. It means what we need to say here is that any starting point x0 in Rn can be written as c times v1 plus c2 times v2 up to plus c3 times v cn times vn. Okay, and again it means that if I apply this to this discrete dynamical system, it means x1 can be written as a times x0, which is a times lambda c1 times v1 plus a c2 times v2 up to a cn times vn. Okay, now it means that I can move that inside here, c1 as av1 plus a c2 av2 and plus cn avn. Okay, we know because this is the eigenvectors, it means this one is c1 times lambda tan v1 plus c2 lambda 2 v2 and cn lambda n v. Similarly, if we do the next iteration, which is x2, this will become again as we multiplied by a, and av1 is again is lambda 1 v1, so that becomes lambda 1 square v1 plus c2 lambda 2 square v2 plus cn lambda n square vn. Similarly, means that xk can be written as c1 lambda 1 to the power k v1 plus c2 lambda 2 to the power k v2 and cn and lambda n to the power k vn. Now this we have to remember that any uh, any vector of a dynamical system can be represented in terms of the matrix that defines the dynamical system, which is A, okay, and corresponding eigenvalues and eigenvectors. Okay. So we apply these concepts to what we know as a predator-prey system. So there are in a predator-prey system that we have rats and owls. So what happens is that owls hunt for wood rats, um, and almost majority of the food that is available to owls are coming from the rats. So owl is actually is the main predator of rat, and in this case rat is then becomes a prey. Okay. Now we have an equation that model the dynamicity of the population of owl and rats in the jungle. So if we say defines a vector x of k, which is ok and rk, it means ok is the population of owl at time k, and r is the population of owl at a population of rats at time k. Okay, and where k is the time in months. K is the time in months. Okay. Okay. Now the dynamical system that characterize this population, as like in the other examples of rude and urban population, we have that the old population increases 0.5 k and 0.4 rk, and r of k plus 1 is minus p times ok plus 1.1 times r of k. Now it's saying that the population of p here is the positive parameter. P is positive here, and why it's positive we'll see that in a moment. The 0.5 rk means that there is no wood rats for the food. So also it means only half the population will survive each month. Okay. While in the second equation we have, if there are no owls, it means if OK is for example 0, it means that the population of the rats will grow by a factor of 1.1 each month. Okay. Now so if the rats are plentiful, so if there are plenty of rats here, right, what will happen is that 0.4% of the rats will actually make the owl population rise by becoming the prey to these owls. And similarly, because uh, uh, r of k is r of k is equals to 1.1 rk, or a rise 10% each month, right? So it means since owl is preying on the rats, it means the owl population that is hunting the rats actually contributes to decrease in the population of the rats. Okay. So what we have to determine is the evolution of the system using eigenvalues. So let's say if let's say p is equals to 0.104, then you have the eigenvalues of this matrix is which is A matrix. I can write this as 0 0.5, 0 0.4, minus 0.104 and 1.1. Okay, now in this case the eigenvalues will become as determinant of A minus lambda I, and which is A 0.5, 0.4 minus 0.104, 1.1 minus lambda, and you take the determinant of this whole matrix. Okay, now when you do that and you find out the corresponding eigenvalues, you have lambda 1 is equals to 1.02 and lambda 2 is equals to 0.58. Okay, and then you can plug in those values as we have done in our previous lectures and calculate the corresponding eigenvector v1 as 10 and 13 and v2 as 5 and 1. Okay, now since we already shown you that any x of k can be written as c1 lambda 1 to the power k, and again v1, and then we have c2 lambda 2 to the power k and v2, because there are only two eigenvalues here, so there will be two eigenvectors, so that equation can be reduced to only two variables here. So in this case x of k, because lambda 1 we assume is has to be greater because you are arranging them in descending order. c1 is 1.02 to the power k into v1, and again c2 is equals to 0.58 to the power k into v2. Right, now what you can see here is as k approaches infinity, it means we are interested in the steady state behavior of the system. If k approaches infinity, it means what we have here is that the population of the owls actually and the rats. Okay, before we do that, so if k approaches infinity, it means this term will keep on increasing, and if this term will keep on decreasing because it's less than 1, right? So this will keep on increasing and this will keep on decreasing. So we can say that as k becomes large, x of k is dominated by c 1.02 to the power k into 1013, which is v1 over here. Okay, so you can actually now think of the problem as over here as well, even the so x of k plus 1, you can write this as from that thing here is c1 into 1.02 into 1.02 to the power k and 10 and 13. So this can be written as x of k plus 1. So this is including that one is nothing but the previous state, which is now 1.0 times x of k, or in this case is lambda 1 times x of k. So in this situation, the steady state behavior when k becomes large is dominated by the first eigenvalues. So we can easily now say about the steady state behavior of any dynamical system, that if x of k plus 1 define x of k as a discrete dynamical system, and the corresponding eigenvalues are lambda 1 up to lambda n, and if you arrange them such that in descending order, and let's assume that lambda 1 mod of lambda 1 is greater than 1, and the rest of the remaining are less than 1, lambda j less than 1, j is equals to 2 up to n, then the steady state behavior of this dynamical system will be can be approximated by x of k plus 1 is equals to lambda times x of k. Okay, now so this is how we can actually understand the behavior, the steady state behavior of a discrete dynamical system, okay, using the eigenvalues and eigenvectors. So what in fact this does is it means that x naught, when we write x of k plus 1 a into x of k, it means starting from x naught, you move on to x1, then you move on to x2, then move on to up to x of k, and then xk plus 1. It means there are a set of points that are formed in Rn, in Rn, and all these, when you trace those points, actually what we now know is the trajectory, of this state, or the trajectory in this case, in the case of predator all system, is the trend of the population that we have in the jungle. Now, so let's say if you have a is equals to 0.8, 0 and 0 and 0.64, the eigenvalues corresponding to this one is, again, we know it becomes simple that lambda 1 is 0.8. For diagonal matrix, it's quite easy to calculate the eigenvalues. Lambda 2 is 0.64. Okay, and the corresponding eigenvalues, eigenvectors, we can find it as 1 0 and v2 as 0 1. So in this case, if A defines a discrete dynamical system, we can write this x of k is equals to c1 times 0.8 to the power k 1 0 plus c2 0 0.01 point into 0.64 to the power k. In this case, as you can see here, as k approaches to a larger value, all these terms will approach towards 0. In the previous scenario, it weren't approaching towards 0. Okay, so it means if I try to plot those trajectories of the points, so we can have any initial starting point. Let's say if you start from here, what effectively it does is basically it will bring all those points back to the origin. So this is x naught. It means this point will be somewhere as k approaches infinity. Okay, again the arrow indicates the direction which this trajectory is traversing. Again, if you start from here, of course you will have the curve which is more like this. Again, x naught is here, similarly x naught is here. You start from any point in this two-dimensional thing. However, because the two-dimensional case here, what we will do is basically always reach towards 0. Okay, similarly there could be other x naughts as well, x naught again, x naught again, so this kind of system, this kind of discrete dynamical system is called attractive. Okay, now luckily we can see here the eigenvalues are less than 1, right? So attractive system has all the eigenvalues less than 1. But if the eigenvalues are greater than 1, then of course the system becomes will not come to 0. Of course it will deviate away from 0. This kind of system is called repeller system. Repeller. So let's do an example of the repeller. Let's say A is 1.4400 so you can see here the eigenvalues lambda 1 is 1.44 and lambda 2 is 1.2, and correspondingly there will be some eigenvectors which is v1 which is 1 0 and other one is v2 is 0 1. Again, we can write this from our understanding of the problem. It's x of k is equals to c1 times 1.44 to the power k 1 0, and again c2 0 1 into 1.2 to the power k. Okay, again as k approaches infinity, starting from any initial point, as k approaches to a large value, what it does is these values becomes quite large, and effectively this system will move away from the origin. So it means so if you start from any point x naught in the system, again here, start from any point x naught in the system, this will be actually, so if x naught was here, it will moving away here, again it was here moving away, Similarly, point here, you move away again, and so on and so forth, right? So it will repel the origin. Okay, again, all the motion is outwards. Okay. Similarly, we can do another example that illustrate that there may be a saddle point uh, at the origin. Say for example, d is equals to 2 0 0 and zero point 0.5, right? Now the corresponding uh, system, let's say, which is y of k plus 1 is equals to dy of k, the system will have again as the following solution, which is c12 to the power k 10 plus c2.5 to the power k 0 and 1. Okay, now we can see here over here as well, that if I plot this as two-dimensional thing over here, which is y1 and y2, starting from initial point x0, right? Now this term will effectively dominate, and this term will effectively approach in the second dimension, will approach 0. So it means starting from any point, there will be decrease in x2, and there will be, or on this side, and again we keep on here, then again we have this again thing over here. So in terms of x1, if write this x1 or x2, should be writing y1 and y2, not y1 and y2, because that would confuse with that one. Let's say x1 and x2, and again similarly we move here at the origin, and it will come back. If the starting point is here, so it means the resultant will be on x2, the resultant will be always approach towards 0. Similarly, if minus x1, it will approach towards here. Now on the negative hand side, we start from here. On the negative, if this is negative, so it means you will have increasing on the negative hand side over here, and again on that side, start from here. Similarly, start from here, you will have this kind of situation in here. Similarly, you will have here as well. So any non-zero x2 will effectively make this system sway away towards x1. If by any chance x2 is 0, it means x1 is 0, then of course this term will effectively start with the factor which has x1 here, approach towards 0, which is we can see from here. Okay. Now there are so far we have seen the systems with the diagonal matrices, but there are scenarios where the system may not be exactly diagonal. So we know that we can actually diagonalize a matrix, and of course it will not change, diagonalization of the matrix will not change the behavior, the steady state behavior of the system. So to handle the non-diagonal case, we can actually go back to our previous understanding of diagonalization. So we say that there are eigenvectors of A that form basis set, which is v1 up to vn for Rn, and we know that we make a matrix P for diagonalization, which is v1 up to vn, and D we know is the diagonal matrix. So if x of k plus 1 is a times x of k, then we can define a new sequence, which is y of k is equals to p inverse x of k, and of course correspondingly x of k is equals to p times y of k. Now again, from the similarity condition, from the similar matrices, we know y of p, if I multiply with this y p, then v of p into yk plus 1 is nothing but something like a p y of k. Okay, substituting this thing over here, so you got here is a p times y of k, because we know that two matrices from the similarity definition of two matrices. Now this can be written as p d p inverse times p times y of k, which is now we know the diagonal matrix, which is p d times y of k. Then y of k plus 1 can be written as, if it apply p inverse from both sides, becomes d times y of k. So the thing what we are trying to say here is that now y of 1 into k plus 1 and y of 2 into k plus 1 can be written as y of n into k plus 1 as lambda 1 to lambda n, and again you have y1 of k up to yn of k. So to demonstrate that how it is useful for finding the steady state response of non-diagonal for the system defined by non-diagonal matrix, we can you can do an example which is in which a is equal to 1.25 minus 0.75 minus 0.75 and 1.25. Okay, so here we have x of k plus 1 is a times x of k. So eigenvalues of a we know here in this case is quite simple, which is comes out to be 2 lambda 1 is equals to 2 and lambda 2 is equals to 0.5. The corresponding eigenvectors is v1 is equals to 1 and minus 1. We know that how to calculate those, so we don't need to I don't need to repeat that again and again. Now since we know that the eigenvalue one of the eigenvalue is greater than and 1, and other eigenvalue is less than 1, and the origin is a settled point, which is x of k is equal to c1 2 to the power k v1 plus c2 0.5 to the power v2. We have already shown that this is kind of system exhibits a saddle point, only it moves away towards x1 only for the point starting point which lies on this x2 axis. The system will converge to 0. For all other points it will actually move towards x1. Okay. Now we can study this problem of steady state behavior in scenarios where A has complex eigenvalues. And now if A has complex eigenvalues, then it becomes we know that is actually kind of rotation that we get from this from the matrix A. So let's say if let's say that if A is point 0.8, 0.5 minus 0.1 1, Okay, now in this case eigenvalues has 0.9 plus minus 2 iota. The eigenvalues, two eigenvalues. Now if there are two eigenvalues and their corresponding eigenvectors are actually 1 minus plus 2 iota and 1, it means for the plus value you have a negative here, and for the negative value you have a positive over here. So it means x of k plus 1 into a times x of k. So initial vector we can assume as 0 or 2.5 or 3 0 and 0 and minus 2.5. Okay, now if we do that, then we have the following graphs that is stemming from these three initial initial points. So if I let's start with 0 and 2.5 over here, what you get here is this kind of rotation over here and coming back to the origin. Now if I choose the second point, which is over here, again to do the same kind of behavior, more or less the same kind, and come back to origin. Similarly, if we have x naught 0 2.5, which is over here, so the result will actually move on, rotates, and kind of making a spiral for the C scenarios. Okay. Yeah. So in this lecture we have seen how eigenvalues, eigenvectors can be used as as to study the behavior of the steady state behavior of dynamical system, and how eigenvalues can be used to to see the trajectory of the states that we're going to have in dynamical system. Thank you.